All right, so welcome back. Last day we did the Lewis dot I say Lewis dot, I mean electron dot diagram for magnesium and bromine. Today we're going to look at three more. We have lithium and fluorine, potassium and phosphorus, and then on this slide, a tricky one, aluminum and oxygen. So let me maybe do something a little different than I did this morning. I'm going to do potassium and phosphorus. Okay, so first let's write down the group number. Potassium is in group 1 and phosphorus is in group 15. So that means potassium would have only one valence electron and phosphorus would have 5. Okay, now the next thing you need to do is come up with some combination so that all of the octets are full. Oh, just hold on one second, guys. Dog's going crazy. Hold on one second. All right, okay. So here I have one electron on the potassium. Oops, sorry. And I have room for 3 on the phosphorus. So what I would need to do is actually have 3 phosphoruses in this formula to balance all of the octets, or give everything all the electrons it needs. So let me pick a new color. What I would do is I would write potassium in square brackets, and I'd put the plus sign out here. I would write phosphorus in square brackets. 1, 2, 3, 4, 5. Now, phosphorus has been full or filled by 3 potassiums. So I give this a full octet. And I would write 3 minus over here. Now, in terms of balancing, this isn't completely correct because I need to make sure I illustrate that I have 3 potassiums, and I could put them around, on the left and on the right, or on the top on the right. But all you really need to do is put a 3 in front of this to show that I have 3 potassiums, and then that balances with 3.
Mister, why it's a 3 potassium?
Okay, so go over, look at the left. Okay, I am adding 3 electrons to this from 3 different molecules. So I need 3 potassiums to give me 3 electrons to fill phosphorus. So I have 3 potassiums. I need 3 over here. This also, by the way, tells me my chemical formula for potassium phosphide, which would be K3P. Also, if you add up the charges, I have 3 positive charges and 3 negative charges, so it's all balanced. So what I would like for you guys to do is to try this one. And on the other slide, there's it asks you guys to try aluminum and oxygen. You can also try these as well. So I'm going to pause myself, and I'll be back in a couple of minutes to see if any of you guys have tried lithium and fluorine and aluminum and oxygen. So I'll be back in 2 minutes. Oh. All right, so lithium and fluorine may be one of the easier ones because it's just straight up, 1 and 1, 1 positive, 1 negative. Lithium is in group 1, fluorine is in group 17. So lithium would look like this, and fluorine would look like this. And as you can see, this is like the perfect match because here I need 1 electron, here I have 1 electron. It's perfectly balanced. We have the lithium positive and fluorine negative, and I'll put my electrons around fluorine. So guys, if you look at this mathematically, +1 and -1 perfectly cancel. So my formula for this chemical compound would be LiF. Here it was K3P. Well, and this will kind of mean something soon, because when we're doing naming or writing names or writing chemical formulas, we need to know the formula. So, and this is kind of where it comes from. Someone in the chat, Warda, says that they have a question. Ask away. So the question was, for the second potassium, can we write 3+? No, you cannot, because the charge on potassium is only +1. It's not 3+. So what I need is I need 3 potassiums to balance out my 3 negative over here. But I can't write 3 positive because potassium is only +1. If you're wondering why it's +1, just look at what happens over here. When you lose an electron, you become more positive, and potassium only has 1 electron to lose. All right. Iman, another question then is, why is this 3 negative? Well, again, look at the phosphorus. Okay, the phosphorus gained 3 electrons, just like we did in chapter 1. So because it gained 3 electrons, it becomes 3 minus. Potassium loses 1 electron and becomes +1. This, again, it really goes back to what we did in chapter 1, where we were like, talking about protons versus electrons and calculating the charge. All right, so this is a tough one. Aluminum and oxygen. All right, so first things first, aluminum is a metal in group 13 and oxygen is a non-metal in group 16. So aluminum looks like this, 1, 2, 3, and oxygen, and I'll do oxygen in another color, looks like this, 1, 2, 3, 4, 5, 6. Okay, so now we have a problem. The aluminum has 3 electrons it wants to give away, but the oxygen can only take 2. So again, think about the problem here. These electrons can't just vanish, they have to be transferred. Aluminum has 3 to give away, oxygen only has 2 spaces to accept. All right, so we got to do some math here. How are we going to get the positive and negative charges to be equal? I have 3 electrons versus 2 electrons. The easy idea here is we need to find a lowest common multiple. Sophia has it correct in the chat. We're going to basically change this scenario so that we now have 6 electrons. That would be your lowest common multiple for 3 and 2. What I mean specifically is, if I had 2 aluminums, that would give me 6 electrons to give away. And if I had 3 oxygens, that would give me 6 electrons to take in. So you need to come up with a number so that the positive and negative cancel. Now, if that still doesn't make sense, just watch what happens when I draw this out. So I'll go with blue. Okay, so the aluminum, each aluminum ion has lost 3 electrons, and each oxygen ion has gained 2 electrons. So the problem here is I need the positive side to equal the negative side. Now think about it. If I had 2 aluminums and I had 3 oxygens, my charges would cancel. So the answer to this question is, I need to figure out the number to put in front of these. I would have 2 aluminums and 3 oxygens. So my formula for this, as Sophia wrote in the chat, would be Al2O3. We will practice this throughout this whole chapter. So if anybody's really confused right now, don't worry. I'm going to show you some tricks on how to come up with this. That's kind of the point of this chapter. Okay, cool. So let's move on. I only have one topic left that I want to do. And then that's it. It'll probably only take us 5 or 10 minutes. So before I get into anything too crazy, I just want to talk about the properties of ionic compounds. And I'm going to stop at this slide. This slide is where we're going to start working on naming. So how to write down the names, the formulas. That's a kind of a good place to stop for today. So let me just very quickly explain some properties and we are done for today. All right. Just want to make sure I'm at the first slide. Okay. Ionic compounds. So there's two types of compounds we're going to talk about in chapter 3 in detail. Ionic versus molecular. So we'll talk more about molecular in another section. But ionic compounds are kept together by electrostatic attraction. So, I mean, you can almost think about it like a magnetic attraction. They're obviously not the same thing, but think about how when a magnet gets close to a metal object, there's a magnetic object, there's some attraction there. Well, cations and anions have a similar attraction. It involves their electrostatic differences or the charge differences. Positive and negative ions are attracted to each other. And because of the high level of attraction, this gives us a few interesting properties. The first is that these compounds form very, very rigid crystal structures. And that's why most solid, or well, almost every ionic compound that we have in the lab, for example, is a solid crystalline material. Like, think of salt or sugar. Now, sugar is completely different, but that's kind of what you can think about, these little crystals. For the students who have done the lab already, you guys saw a lot of these crystals up at the front when you looked at like the purple one and the green one and the blue one. They were crystal structures. So the thing is, in a single crystal of, say, salt, you can have hundreds and thousands and millions of ions. And we don't want to count them all when we write the formula. So what we do is we write what's called a formula unit, which is the lowest whole number ratio of the elements. Now that sounds really complicated, but it's really not. For example, in sodium chloride, which I have right here, it's a 1-to-1 ratio. If you have 8,314 sodiums, you will need to balance that with 8,314 chlorines. If you have a million chlorines, you need a million sodiums. In the previous example where I had Al2O3, this would be a 2-to-3 ratio. So if I had 2 million aluminums, I would need to balance that with 3 million oxygens. And I'm saying million because, in a teaspoon or a cup of salt, you have billions and trillions of ions because they're so small. The reason I'm telling you this, by the way, is because this is very different than how molecules work. So we'll kind of keep this in mind for the rest of this chapter. All right, only really two properties left. Again, because the ionic compounds are very rigid, tough crystal structures, they have a really big melting and boiling point. MP means melting point, BP means boiling. Okay, so like, water. Water melts at 0 degrees Celsius and water boils at, 100 degrees Celsius. Let's just check out the melting point for NaCl. The melting point for sodium chloride is 801 degrees Celsius. And that's not even that high. You can get them much higher than that, in the thousands of degrees Celsius. So ionic compounds have very high melting and boiling points. Now, this is the last thing I'm going to talk about today. Ionic compounds also conduct electricity. But in order to conduct electricity, two properties need to be met. One, electrons have to move from one atom to another. And two, there must be positive and negative charges that can also separate to create a difference in charge, which allows the electrons to flow or move from one atom to another. Now, you guys do not need to memorize this, okay? But it is good to know for the future. If you do chemistry 2, electrochemistry, you will talk a lot more about this. But what you should know is that an ionic, it's like electrolysis, somebody had mentioned in the chat. Oops. But luckily we're not going to do that in this course. But electrolysis is typically when you apply electric current to make a reaction happen. Then you can have like electrochemical reactions that are spontaneous, meaning you don't need to put electricity in, and that's how batteries work. So yeah, this is a pretty interesting topic, but unfortunately we won't get to it until chemistry 2. Anyways, what you should know are these two things. Ionic solids can't conduct electricity, and that's because the electrons in ionic solids are strongly held into place. So in order for an ionic compound to be conductive to electricity, it needs two things, or it needs at least one of two things. It needs to be dissolved in water or melted into a liquid. And in each of these, I kind of want to say phases or situations, now that we have it dissolved in water or melted, it means electricity can conduct, electrons can move throughout the medium. So I have a little picture here. I think, yeah, this is the last slide. A little picture here of, it's a lamp or a light bulb hooked up in the same way to 3 different states, I guess, of this ionic compound. In the solid, nothing happens. When we melt it or turn it into a liquid, however, it does conduct electricity. So solid, nothing happens, but when it's molten, which means melted, it will conduct electricity. And when it's dissolved in water, it will definitely conduct electricity. All right, so that's it for the properties of ionic compounds. If you guys have any questions, let me know. Other than that, I'm going to hit stop record and get ready for my lab.